In this video, we put our graphing skills to use as we solve polynomial and rational inequalities. Let's get started. So imagine you have a graph like the one on the screen. It looks like this graph breaks apart at a certain location, maybe at a vertical asymptote, and the graph now has two pieces where it exists. How would you answer the question if this is called y equals f of x? This is your function, y equals f of x. Well, the question is, when is f of x less than or equal to 0? What does that mean? When are your outputs below the x-axis or equal to 0? What inputs, in other words, would make that happen? Well, looking at the graph, can you tell where the graph is positive, where its outputs are above? Yeah, that would be up here, wouldn't it? In this piece, on the left in quadrant 2. However, to answer the question, when is the graph below the x-axis, where do you think it would be? Yeah, that's right. It would definitely be to the right of the asymptote, which happens at x equals negative, looks like 1. So it looks like at x equals negative 1, I have a vertical asymptote. So if I'm to the right of that asymptote, but not including it because it wouldn't actually exist there, we would say this is happening to the right of negative 1, so parentheses negative 1, but it only continues to be below the x-axis until we get to the X-intercept, which occurs at 2. So what I notice is that between the vertical asymptote and the x-intercept, we're satisfying the conditions for our outputs being less than or equal to 0. So I would say from negative 1 until 2, but I'm allowed to equal 0 for an output, so 2 as that input would be appropriate to exist. So I would say brackets instead of parentheses. So what this solution is saying is all inputs bigger than negative 1, but up to and including 2 would create outputs which are either negative or 0. Okay, so for example, if this was a business, this might indicate when you have $0 left or you're in the red. Okay, so you would want to avoid these inputs. All right, well, let's go ahead and now look at an example where instead of me providing you with the graph, you have an inequality written almost like an equation, but with the less than or greater than symbols. And let's see how we would approach this. So consider with me on the middle of the screen here, x squared minus 8x is greater than or equal to negative 7. First, I would like you to identify what type of inequality this is. For example, is it linear? Is it a quadratic inequality? Is it just a random polynomial with some other degree? Or maybe a rational inequality? You're right, this is a quadratic. It's a special type of polynomial where the degree is 2. So we know what these look like. They're typically called parabolas, right? But in general, whether you have rational, which is a fraction, or a polynomial with no fractions, you still want to follow the same process when you're trying to analyze graphically the inputs which make this true. So the first step, get 0 on the right. Technically, you could get it on either side, but the right side is going to make more sense to our brains. So for example, step 1 here would mean that x squared minus 8x plus 7, when you move it to the other side, must be greater than or equal to 0. Next, we want to go ahead and graph, right? We want to graph the function which is on this side of the inequality, on the left side of the inequality. So I notice here for step 2 that I need to graph it, and the easiest way to graph it is if I knew the intercepts, like X-intercepts or Y-intercepts. Now, if this was a rational function, then I would need asymptotes, but this one is a polynomial. There's no fraction, so there's no issues with their denominators, right? So we would simply say, how could I graph a parabola, a degree 2 polynomial? Well, I can factor that, can't I? So my second step, in order to graph it, I first get the x and y-intercepts. So I need to factor factors of 7 with the same sign that add up to negative 8. You're right, x minus 1 and x minus 7 must be greater than or equal to 0. Okay, so what would be the x-intercepts from each of those factors? We've studied polynomial graphs in the past. If this is f of x equals x minus 7 times x minus 1, what are my two x-intercepts? That's right, x could either be 1 or x could be 7. Both of those would zero out the function. They're called real zeros of the polynomial. So I could go to my graph, these are my x-intercepts or my real zeros, and I could put those x-intercepts on the graph, 2, 3, 4, 5, 6, 7, there we go. Now, is this polynomial a polynomial that is going in the same directions at the extremes? Different directions at the extremes? And how do we determine that end behavior? That's right, we look at the degree and the sign of the leading coefficient. The degree of this polynomial is what? 2, which is even, so we're going in the same directions at the extremes. And then the leading coefficient looks like it's just a 1, whether you're in expanded form like originally here, or in the factored form, you're still having a leading coefficient of positive 1, which means instead of going down in the extremes, we're going up in the extremes. So we could simply draw a parabola. Because it's degree 2, we know it's a parabola. We also know that the multiplicity of each factor will tell us whether we're touching or crossing the x-axis. Remember that if the multiplicity was even, we touch and turn around, but if it was odd, we cross or cut through. So we look here, we see that each factor has an implied multiplicity of 1, which is odd. So what should I do? I should be crossing the x-axis. So I cross through the x-axis, and you're welcome if you want to show off your parabola graphing skills. You could even find that vertex, that lowest point for a degree 2 parabola, by finding negative b over 2a and then plugging it into the function to find your y-coordinate. Okay, one other thing you could find, in addition, if you really wanted to show a good sketch, you could even find a y-intercept. And how do we find y-intercepts? Well, instead of letting y equal 0, we let x equal 0. And if x equaled 0 in the original, 0 squared minus 8 times 0 plus 7, what would we get? That's right, it's just 7. So at 1, 2, 3, 4, 5, 6, 7, I hope I counted that right, we'd have a sketch of our parabola there, and we could also go the other direction and have a parabola looking something like this. Okay, it's just a basic sketch. All we really needed, though, the bare necessities, if you will, we needed the intercepts. And by intercepts, predominantly, we needed the x-intercepts. By having those, we're going to be able to now tell when the graph is above or below the x-axis. What are we looking for particularly in this case? In this case, for step 3, we're looking for when the graph is greater than or equal to 0. That would mean above or on the x-axis. If it was strictly greater than 0, we strictly would want outputs which are bigger than 0 or positive numbers. But in this case, 0 or higher. We just don't want to be in the red, if you will. So that would include any x input. You can do it yourself, maybe pause the video and try it, see if it's the same as me. Any input to the left of x-intercept 1, and any input to the right of the x-intercept 7. Those would both create outputs which are greater than 0. Since we're allowed to equal 0, I can also include those inputs 1 and 7. Meaning my solution would be, when am I above or on the x-axis? Any input to the left of 1, so that would be negative infinity until I get to 1. I would use a bracket because I'm allowed to exist at 1, since that would create an output of equals 0. Or the union symbol, any input starting at 7 or higher, 7 to infinity, using brackets indicating I can have an input of 7 because that creates an output of 0, which is allowed. Okay, so what this would tell a business, for example, is I would need to set my price point or whatever it is I'm looking for 1 or less, or 7 or higher, so that my output, maybe my profit, would be at least 0 or higher. I'm not owing any money. Okay, so that's the kind of idea of reading a graph for inequalities. You're trying to determine appropriate inputs to give you the outputs that you're interested in. So go through this slide again. Make sure you have the steps really clear in your head. If you're going to be solving an inequality, first step, get 0 on one side. Second step, graph the equation on the left as if it's a regular equation using intercepts, and if it's rational, also with asymptotes. Finally, answer the question, when is the graph above, below, or on the x-axis? All right, let's go over to another one and see how you're doing. Suppose you have the inequality x times x plus 2 in parentheses squared. When is that inequality, or when is that side of the equation, less than or equal to 0? It says write your solution in interval notation. So if you wanted to solve this graphically, first step from the last slide was get 0 on the right. They've already done that for us, so we can say thank you and move on. Okay? If that wasn't a 0, I would have to move everything over to the other side before I proceed. The next step was to, that's right, graph using intercepts. Since this is already in factored form, if you have f of x equals x times x plus 2 to the second power, what do we know about x-intercepts if we have factors? That's right, x is either 0, or here x is equal to negative 2. Those are my two x-intercepts for this polynomial inequality. I could go to the graph and plot those, 0, 1, 2. So those are my two x-intercepts, 0 and negative 2. Now to continue the graph, we would look for end behavior, wouldn't we, for a polynomial? We'd look for end behavior. So we have to ask ourselves, what is the degree of this polynomial? Well, it's in factored form, so I don't just look for the highest power, but rather I add up the multiplicities of each factor. 1 plus 2 is 3, which is odd. So at the extremes, am I going in the same directions, or different directions? That's right, different directions. Now, how did I determine if it was increasing or decreasing from left to right? I look at the sign of the leading coefficient, which is implied 1, a positive, in fact. So I should be increasing from left to right, almost like the graph y equals x cubed, like the snake, increasing from left to right. So something like this and something like that. So we have a basic idea there. Now in the middle, what's happening is determined by the multiplicities of each factor. At -2, for example, the multiplicity there was 2, which would be representing an even number, and even numbers mean I touch and turn around. So you'll watch my graph approach -2 from the left, and then after it hits -2, to the right of that, I should be turning around. Then I noticed that for the next x-intercept of 0, it came from this factor, x, which had a multiplicity of 1, which is odd. So I should be crossing through. So I'm going to have to turn around somewhere. In calculus, you'll learn where exactly you turn around by finding something called a derivative, setting it equal to 0. But for now, we don't know that, so we're just going to turn it around somewhere. We don't know where it turns until we get to calculus. So hopefully that encourages you to want to study calculus. Okay, so we have a basic idea here of a graph that is going in different directions at the extremes, crossing the x-axis at both -2 and 0. And it also turned out that's my y-intercept at 0 as well, because you can only have one y-intercept. If it's at the origin for an x-intercept, that's also your y-intercept, 0, 0. Okay, so we have a very, very basic sketch. All we care about to solve this inequality, for step 3, if you will, we care about finding out when is our function less than or equal to 0. Less than or equal to 0 means our output should be negative or 0. Well, that occurs left of the x-intercept -2, so I could say parentheses -infinity until -2. Am I allowed to equal -2? In other words, can my output equal 0? If so, then I can use this input. Well, the output must be less than or equal to 0, so yes, I can include that input. So I use a bracket. Union, if I have another piece, am I ever again going to be less than or equal to 0? Wait a second, we're actually less than or equal to 0 again, between the two x-intercepts. So you could say union -2 with the bracket to 0 with the bracket. You could definitely say this. But does it look a little interesting to anyone besides me? -infinity to -2 bracket, union, bracket, -2 to 0. It kind of looks kind of strange, because isn't it saying you can be anything left of -2 and including -2, or you could be anything right of -2 until 0, but including -2. In both cases, aren't we including -2? We are. So couldn't I just say from the entire interval, -infinity to 0, like this, -infinity until 0? I could. That would be the cleaner way of saying this, okay, the better way, because you don't really need to say stop at -2 and then continue. You actually existed there. The only time you need to separate them, like a first did, was if you had an open circle situation. For example, if this was strictly less than 0, but it's not. It includes 0, so you're allowed to include the -2 and continue along. So I would say the best answer would be any input 0 or less. That would be the easiest way to describe the situation for this business, if you will. Okay, so I've done a couple of examples of polynomial inequalities. Next up, let's take a look at a rational inequality and see if you can apply the same algorithm to this situation. And again, you're welcome to pause the video and give it a shot yourself. It says 3x plus 3 divided by 2x plus 4 is greater than 0. So if I was solving this by the graphical method, which is what I've done in this video so far, I would first need to find that 0 is on the right side. Okay, and they have done that for us, so we're very fortunate. Keep in mind, in some of your homework practice, you might have a number there or another fraction on the right side. You would first need to subtract it or add it to the other side, so change the sign, and then you would have to get a common denominator to combine the two fractions that are being added or subtracted. So make sure you have really good skills when it comes to adding and subtracting fractions by finding the least common denominator. If you don't have solid skills there, especially with distributing signs and such, you're going to be having a difficult time doing these types of situations, solving these types of inequalities. Okay, so I gave us an easy one. You're welcome, maybe. In this case, we're going to first notice 0 is on the right side. So I'm able to begin the process of finding any x-intercepts. That's what we did last time, right? X-intercepts. Okay, to find an x-intercept, we typically let y equal 0. So if I let y equal 0, the entire output here, f of x if you will, equals the left side, right? 3x plus 3 divided by 2x plus 4. Okay, so if I let y equal 0, wouldn't that mean that the entire numerator equals 0? because the only way that a fraction, something divided by something, equals 0 is if the numerator was 0. Why? Because if the denominator was 0, that's undefined. You can't divide by 0. Okay, so I would simply take my numerator, 3x plus 3, and say, when are you 0? Okay, well, you're 0 if 3x equals negative 3. And that's going to happen only if x equals negative 1. So the only time, this is really important to conceptualize, the only time your graph will ever touch the x-axis will be at the value negative 1. So keep that in mind. It's a very important concept to understand. Not just go through the motions and put it on the graph. Understand that's the only time that you can cross that x-axis. Okay. Similarly, we normally would find y-intercepts to get a better sketch. So let's go ahead and do that real quick, and then we'll talk asymptotes. To find y-intercepts, on the other hand, we normally let x equal 0, right? So if I were to let x equal 0, that would mean f of 0 in our function. So if you let x equals 0, you would have 3 times 0 plus 3, or just 3 in the numerator, and 2 times 0 plus 4, or just 4 in the denominator. So you're getting 3/4, or 0.75. Go to your y-axis and plot that point. So that's going to be, oh, not negative. Goodness. Grab that. Okay, that's going to be somewhere up here. Okay, so we have an idea now of where the graph is crossing the x and the y-axis based on my intercepts. Okay, what else do I need, though, for a rational function, a fraction here? That's right, I need to find asymptotes. So to find a vertical asymptote, you might need to go back to our previous videos where we discussed how to graph rational functions. What were we concerned with? That's right, when we would have denominators equal to 0. So if you let 2x plus 4 equal 0, what would that mean for x if that's equal to 0? Yeah, that 2x would equal negative 4. So what would x have to be? Negative 4 divided by 2, or negative 2? So I'm going to erase this just for room if you don't mind. You can go back if you need to. We're claiming that x equals negative 2 as our vertical asymptote. But again, conceptually, what does that mean? That's right. That's the place in the graph where you can have no existence for that input. So at negative 2, the graph should break apart. But to show that to the reader, you usually do like a dotted line at that location, right? So x equals negative 2 is our vertical asymptote. We also talked about, in the last video series, we talked about horizontal asymptotes, didn't we? To find a horizontal asymptotes, we compared the degrees of the numerator and the denominator, if they were the same, larger, or smaller. In this case, 1 and 1 are both the degrees of the numerator and denominator. In other words, n equals m. Feel free to go back to your notes or the previous videos to remember what that meant. Didn't that mean that we found that the y equals a ratio of the leading coefficients was our horizontal asymptote? So in this case, the leading coefficient 3 divided by the leading coefficient 2 would give us 3 over 2, or 1.5, as our horizontal asymptote that we're approaching as we go toward the extremes. So we're approaching that output as x gets big and as x gets small. So 1.5, here's 1, here's 2. That's going to be around here. I'm trying to draw a line in between these two numbers. Okay. So that's y equals 3/2, my horizontal asymptote. Based on that alone, we actually could figure out, if we're thinking cleverly, what this sketch looks like without using any technology, which you're welcome to check on Desmos afterward. Okay, so we know that the graph, it can only cross the axes at the intercepts, right? So if I can only cross the x-axis at negative 1, and I can only cross the y-axis at 3/4, then that means that in this region, to the right of the asymptote x equals negative 2, I must be something like this, right? I must be touching both those intercepts and then continuing to get closer and closer to both asymptotes. But on the left side of x equals negative 2, the other piece that we need to consider, we need to know, are we above the horizontal asymptote or are we below it? And how do you think we could figure that out other than just plugging in x values and seeing where we are for our output? That's right. If we're really clever, we could realize that if I'm below it, I would have to cross the x-axis. But that would mean I would need another x-intercept. And I only have the one, right? That's why I made that big point about it earlier. Therefore, I can know that my graph must be above instead. It can't be below because it would have another x-intercept. If you don't believe me, try a test point like f of a number less than negative 2. How about f of negative 3? If you plugged in f of negative 3, or plugged in negative 3, I should say, into the f of x function, we would have negative 3 times 3, or negative 9. Add 3 to that, we have negative 6 for the numerator. Well, now it seems negative. Maybe you're nervous. Let's check the denominator. 2 times negative 3 is negative 6. Add 4 to that, and you have negative 2. But a negative divided by a negative is a beautiful positive 3. That means that at the x input negative 3, the y input would be at 1, 2, 3. I didn't graph it perfectly, but it would definitely be positive. It would be up here. So if you wanted to draw it more accurately, let me fix this for you so you can believe me a little bit easier. Okay, grab my color. There we go. All right. So at negative 3, I should be at 1, 2, and 3. That's enough information to really confirm my suspicion. Oops, it should be getting closer and closer to the asymptote, not bouncing back up. But that's a basic graph. All I needed to do was draw a very basic graph, which again took a little bit of time because I was trying to go slowly for us. But now we can answer the question, can't we? The question was, when is this function greater than 0? To be greater than 0 means that I'm above the x-axis. That happens over here to the left of the asymptote, so let's describe that. My solution would be negative infinity until the asymptote of negative 2. Can I ever exist at that asymptote? No, so I would use a parentheses. I need a union if there's another piece where this happens. Does the graph ever go above the x-axis again? Not down here, but it does after the x-intercept negative 1, doesn't it? And to the right forever, it'll get closer and closer to that horizontal asymptote, which is always staying above the x-axis. So I could say any x value to the right of negative 1 toward infinity would work. Now, would I use a bracket or a parentheses this time for negative 1? Well, it's not an asymptote, a vertical asymptote, so I could technically cross at negative 1, that x-intercept, but it asks for outputs which are above 0. So if this was a business model, for example, they want to know when they're starting to make money, not just when they're breaking even at 0. So you would say any x input, which is to the right of negative 1, not equal to negative 1. So my final answer would look something like this. Any x value left of negative 2, less than negative 2, or greater than negative 1. So that's a lot of inputs that are possible, but there are a couple which make this problematic down here, make it negative or 0. Okay, so we've done quite a bit in this video. If you need to work on your graphing skills, go back to our previous videos and make sure you're really comfortable with them. I will tell you that you could also solve inequalities using an algebraic method, which you'll see if you start practicing on your online software. If anyone has questions, always feel free to come by my office or email me. Good luck and happy practicing, because math is not a spectator sport. See you next time.